All right, and welcome everyone to this lecture where we're going to be studying the physics concept of light. Specifically, we're going to be talking about the nature of light, color in the electromagnetic spectrum, polarization, and the scattering of light. So to begin with, we're going to talk about the nature of light. Now, light is a wave, all right? It does all the things that other waves do. It reflects, it refracts, it diffracts, it does all of the natural wave behaviors. But light is also a little bit odd. Light also displays properties associated with particles. Sometimes we can think of light being packaged up into bottles or into packets of energy. All right. Instead of just being free-flowing energy, the energy comes in packets. Okay. Think of the energy as being water coming out of a tap. Okay. So you go into your kitchen, you turn on the sink, and out of the tap flows water. All right, and you can adjust the flow rate of how fast the water's coming out, but the water comes continuously out of the tap. That's how the energy in most waves happens, okay? That it just flows continuously. Now, you can also go to Kroger's and buy a 24-pack of bottled water, assuming that Kroger still has that in stock. So, what's the difference? Well, the bottled water doesn't free flow. It's still water, you still drink it, but it comes in specific measured out quantities that are separate from each other. All right? So water out of the tap, out of the sink versus bottled water. The same thing goes with the energy of all different types of waves versus light waves. In most other types of waves, what we have is free-flowing energy, like the water coming out of a tap. With light, the energy's packaged up. It's bottled up, like those 24-pack of bottled water you buy at Kroger's. All right? So bottles. We call these packets a special name. They're called photons. So the bottled up packets of energy in a beam of light are referred to as photons. You can think of a photon as a particle of light. It has energy, but it does not have mass. Now, Albert Einstein made a very important observation here. He said that all observers measure the same speed of light, okay, regardless of their speed relative to one another. Now, if you're sitting there at this point, shaking your head, scratching your head, going, well, what's going on? That's okay. Physicists are still trying to wrap their head around some of these ideas today. In fact, it took Einstein to start to figure some of this stuff out. Einstein's theory of relativity said that basically the speed of light is the universal speed limit. Nothing can go faster. And even if you're going very, very, very fast, you still see the speed of light as the same. Remember way back when we were talking about motion, and we were talking about relative motion. And if you are driving in a car, and you look over, say you're in the passenger seat of a car, you look over at a telephone pole off in the distance, it's kind of slowly moving past you, all right? But yet, if you're standing outside next to that telephone pole watching the traffic go by on the road, those cars are zooming by. They're moving really fast. It all depends on your relative position, okay? Light doesn't work like that. No matter where you're at or how fast you're going to see light traveling at the same speed. Let's look at an example. Let's say a friend zooms by you in a spaceship, and that spaceship is going at 90% the speed of light. We use the letter c for the speed of light, so she's going at 0.90 c. As she passes by you, going nearly the speed of light, you shine a flashlight in the same direction that she's going, okay? Now that beam of light is traveling at the speed of light. So eventually, as you see here in the diagram, eventually that beam of light overtakes her spaceship, okay? It doesn't matter whether you're you or your friend in the spaceship. You both see the speed of light traveling at exactly the speed of light. Even though she's moving very fast relative to you, your friend sees the speed of that beam of light from your flashlight going at the speed of light. It's not going faster or slower. It's really a weird kind of concept to get your head wrapped around. This also has some unintended consequences in terms of the speed of time. We know that at very high speeds, clocks run slower. And we can measure this. In fact, we can have a very well-calibrated atomic clock on Earth and an exact duplicate on the International Space Station. And as the clock on the space station is traveling around the Earth at a very high rate, we note that it actually slows down a little bit. The time for those astronauts up there is actually going just a few microseconds slower than it is for the rest of us here on Earth. Now, while they're going very fast in the space station, they're not going near the speed of light. As you approach the speed of light, that difference in time gets bigger and bigger and bigger and bigger and bigger. All right, this is the one problem with a lot of your sci-fi movies: going to warp speed, going to faster than light travel. Because if we build a rocket ship that goes faster than the speed of light, and we load an astronaut into it and shoot him off to some distant galaxy, a year for him, let's say he's gone for a year according to his frame of reference, traveling at the speed of light. When he comes back to Earth, 100 years may have passed. He may be here looking at the grandchildren of the people he once knew. Time goes much slower the faster you go, the faster and closer to that speed of light you go. Again, all of this is relative to one another, hence Einstein's term, the theory of relativity. Again, this is really some kind of bizarre out there stuff, but a lot of things that we've heard in science fiction and all do have their ground and their basis in true science fact. Now, what causes light? What causes an electromagnetic wave? And that's all light is an electromagnetic wave. What happens is we have an atom that oscillates, that vibrates back and forth. If you remember from our initial study of waves, anything that vibrates back and forth causes a wave. So when we have an atom vibrating back and forth, that causes these electromagnetic waves. Electromagnetic waves are made up of an electric field and a magnetic field that are oscillating perpendicular to one another, at a right angle to one another. Okay? Now, electromagnetic waves, again, are produced in nature when an electron in an atom oscillates back and forth. Light waves are just one specific type of electromagnetic wave. The frequency of an electromagnetic wave is key to its behavior. We only are able to see certain frequencies of electromagnetic radiation. That's what we call visible light. All right? But there's a ton of other types of electromagnetic radiation out there. You already know what they are. You probably already covered them in your physical science class. Now, when we talked about waves, we talk about wave speed. And we said that the velocity of a wave is equal to its frequency times its wavelength. Well, the same holds true for electromagnetic waves, except this time the speed never changes. It's always going to be the speed of light, which we use the letter c. So in this case, the wave speed for an electromagnetic wave is c is equal to frequency times wavelength. Here we have just a general outline of the electromagnetic spectrum. We have radio waves on the far left. They are the lowest frequency. All right, longest wavelength. We're bombarded with radio waves our entire lives. They're completely harmless. We use them a ton for telecommunications. Radio waves are very important. Right up above radio waves are microwaves. All right, microwaves, again, we use them to cook food. That's what a microwave is. We also use microwaves in cell phones and Wi-Fi connections. That's all microwave radiation. Infrared waves, right above microwaves, right below where we see invisible light. Infra means below, so literally below red, so just before we get to red on the electromagnetic spectrum. Infrared waves are what we use to for those heat guns, where we see like those heat cameras that firefighters use. Your remote control on your TV uses infrared radiation to send a signal to change the channel or the volume on your TV. Then we have our visible light, the color spectrum. Roy G. Biv, the colors of the rainbow. All right. This is the only part of the spectrum that our bodies are able to interpret. Just beyond that, just beyond violet, above violet, ultraviolet is our ultraviolet radiation. UV radiation are invisible to us, but they're the ones that cause suntans. UV radiation is given off by stars and galaxies, and of course our sun. If you buy sunscreen in the summer, it's UVA and UVB block. Well, that's the different types of ultraviolet radiation that are produced by our sun. Going on above ultraviolet radiation are X-rays. Now, we've all had the experience of having an X-ray taken. X-rays in small amounts are not dangerous. Large amounts can be very dangerous. And finally, we have gamma rays. And gamma rays are the most dangerous. Gamma rays can be used to kill microorganisms, so they can be used for good. They can be used to kill cancer cells. If you've never known anyone who has had cancer and did radiation therapy or had radiation treatments, not chemotherapy, but radiation therapy, what they're doing is they're actually going into the hospital and having their tumor bombarded with gamma rays. The gamma rays can be targeted to a very specific spot in the body, whereas chemotherapy that is literally poison that goes all throughout the body. Gamma rays can be focused specifically at a specific site in the body to kill just the tumor cells. If you watch the TV, you'll see commercials for things like CyberKnife and stuff like that. Those are gamma rays that they're using to kill the cancer cells. Now, again, visible light is the only part of the spectrum that we're able to sense. Our cells in our eyes are able to see three different types of color: red, green, and blue. All right. Of course, those are the primary colors, and all the mixtures of those colors are what make up what we see. Here we see our red, green, and blue colors of light, and then our secondary colors in the middle: yellow, magenta, cyan, and when all the colors are mixed together, we have white light. Now, when we look into the sky of a perfectly clear, cloudless day, we see a uniform color of blue in the sky. But not every animal sees that. Bees, butterflies, pigeons see different colors of light because what they do is they're able to perceive different parts of the electromagnetic spectrum than we are. Now, in general, the direction of the electric field in a light wave, or any electromagnetic wave, but let's focus in on visible light. The direction of that electric field is referred to as what we call its polarization, its direction. So here we have a picture of two different light waves. Picture A has the electric field oscillating up and down in the vertical direction. So we would say that it is linearly polarized in the vertical direction. Picture B has the same type of light wave, but it is polarized at a 30-degree angle. So we can have light waves polarized or moving in all different directions. So here's another picture to kind of represent this. Picture A shows vertically polarized light. Picture B shows what we call unpolarized light. That's light that with light waves and electromagnetic waves coming in all different directions. All right. So an incandescent light bulb, the sun. These are all examples of sources of light that produce unpolarized light, light that goes out in all directions. Now, we can take that unfiltered, unpolarized light, the light that's just going off in all different random directions, and run it through what we call a polarizer. Basically reduce it down to only moving in one direction. So here we have a couple pictures. We have a vertical polarizer, all right? The wave displaces, goes through that vertical polarizer, and so it's only allowing that vertical wave to travel through. In picture B, we have the slot moving in the opposite direction. It's horizontal. So what happens to that vertical wave? It gets stopped. Do you see that? See in picture A, the wave's coming through. Picture B, there is no wave coming through. It's just a straight line. That's what a polarizer does. It allows certain directions of light through and stops every other direction. So if we have an incoming beam of unpolarized light, we run it through a polarizer, what we get on the other side is just one direction of light, not all those different random directions. And you say, well, who cares? Why would we want to do that? Well, there's a lot of practical uses. Engineers will build a plastic replica of a bridge or a building, and will study the stress in its various parts using a technique called photoelastic stress analysis. Basically, they look at it, they shine a light on the model and look at that through different polarizations, and that way they can see the degree to which there's different stress, fractures and cracks and things in the material at different points. Dentists will do the same thing when they study stress in teeth. Doctors will do the same thing when they design prosthetic joints. So there's a lot of applications for polarization. And now, a word from our sponsors.
Everybody has sunglasses, but most sunglasses make things darker and are useless when it comes to blinding glare. Not these. Nick Bolton here with the latest from Bell & Howell. We call them tack glasses. Inspired by the sunglasses worn by our heroes in uniform, tack glasses can do things no ordinary sunglasses can do, like block blinding glare so well, invisible objects suddenly become visible. Enhance colors to give you vision as sharp as an eagle's and survive even the harshest conditions. Look, ordinary sunglasses just make things darker, which could be deadly in a tactical situation. But tack glasses improve optical clarity, so you can see clearly even in low light. If you've never seen how this light filtering technology works, check this out. Nothing to see, right? But look again as we hold up our tack glasses. A colorful American Eagle's revealed. Amazing.
Look at the screen.
Yes.
What do you see?
I see a white screen.
Just a plain white screen.
Now look at it through our sunglasses.
Whoa, this is cool.
How does it do that? That is so awesome.
What? Oh my. Whoa, what? That is so cool.
That is amazing. How's it do that?
It's like an eagle pops out of nowhere.
Very, very cool.
Whether you're on the trail or on the golf course, on the water or on the slopes, with tack glasses, you'll always see clearly without any glare. There's just nothing like them on the market today.
Okay, so I didn't show you that commercial just for the heck of it. That commercial actually has some pretty good information in it. Polarized sunglasses, that's how they work. There's a polarizer in there that's only allowing certain directions of light through. So, they show that white screen to the people that's just all different random directions of light. But behind that is a picture of an American Eagle that's been polarized. It's only in one direction of light. So when they put on the sunglasses, all those other random directions of light are being filtered out, and miraculously you see the American bald eagle. That's how polarization works. Now, there's absolutely nothing special about those particular sunglasses. You can buy any pair of polarized sunglasses and it'll do the same thing. That's the principle. Now, light is often polarized when it reflects from a smooth surface, like off of water, all right? So the sun reflecting off of a lake, all right? That light is horizontally polarized when it gets reflected off the lake. So, when we buy sunglasses that say they reduce glare, what they actually have is a polarizing filter inside of them that reduces the amount of horizontal light that you see. Therefore, it's stopping that glare light that's in that horizontal direction from hitting your eye. That's all it is. So there's nothing special about polarized sunglasses or those tack glasses that you saw in the commercial. It's just polarization. It's just running light through a filter. That's it. Alright guys, so that takes care of certain behaviors and characteristics of light. If you have any questions, let me know.